All right, let's look at some practice problems. In this case, we have tracking that we're trying to accomplish. And so, again, if you have a reference signal and a closed loop system that involves a controller K and some output Y, basically the frequency content of R should be in some low frequency range. We would call that the pass band. And then over here, we have what's called the stop band. And we want the magnitudes to be small in this region because this is the region in which we may have high frequency noise. So again, I have T and K, and so we're looking at what does that mean in terms of the original closed loop transfer function P. Open loop transfer function P and the controller K. So in particular, what does it mean in terms of K? If we were going to design a controller, what does that mean? Well, obviously it depends on P. So here's an example transfer function that we might work with. And so we might have this as a desired closed loop response. So the green is the smallest singular value, the reddish here is the largest singular value, and so we want unit gain for low frequencies and small gain for high frequencies. Okay, so that's the kind of thing we would want. And so that, again, so this is what we desire in the closed loop. What is that going to look like in the open loop? That is for the product PK. And so what we went through and showed is that we want this to be large gain for low frequencies and small gain for high frequencies. And so this is the kind of thing we might look at, we might want. So notice that I have a smallest singular value and largest singular value, and notice that the largest singular value could do all kinds of stuff. So notice that here it like has this very steep peak associated with it. Incidentally, whenever we have very large values in the open loop, that corresponds to places where we have very good either tracking or disturbance rejection. So for example, at this frequency, I would be able to track a sinusoid at that frequency pretty well because it has a very large magnitude response at that point. So in terms of noise, the smaller we can get, the better. Definitely you want it below 0 dB. So that's the kind of thing we want. So in terms of the singular values, this is the kind of thing we would want. That plant I had has this the transfer function has this response. So the largest singular value, smallest singular value. Okay, so if we look back at this response here, this is 10 to the 0. Here's 10 to the 0. So if this is the response that we want for PK, and this is the response we have for P, then obviously our controller is going to have to compensate so that the product of this times K gives us something that we would want. So that would mean the controller K has to have a frequency response that looks like this. It's going to have that peak, and so notice how this continues on here. There's probably an integrator in the system that is giving this kind of a response. So if this is our response of our system, notice that here we know that we're going to need low frequencies, but we notice that our plant actually has fairly low frequencies, fairly low values at high frequencies, so the controller doesn't have to work that hard at low frequencies, at high frequencies, because the plant already is doing that. So our controller can relax a little bit down here and focus on what's going on over here. And so that's the kind of thing we would look at in terms of loop shaping. So here we have not been very quantitative in a lot of what we've been talking about. We have in terms of formulas, fairly complicated formulas, But mainly we want to give you the sense of the kind of thing that's needed in the frequency domain to know what a controller would look like, a good controller would look like for a particular system and a particular reference input and so forth. And this is the kind of thing we would have. So this is loop shaping. Thanks for watching.